Hey everybody, it's Ripley again. We're in chapter 4 now. We're going to do a little probability. Now you may say, Ripley, why are we doing probability? Probability is the engine that drives statistics. It underlies all of the statistical concepts that we deal with when we do statistics. So we're going to spend a couple chapters just kind of putzing around with probability, hopefully taking your understanding of it to a higher level. This textbook may use different definitions, they may use different terminology, but I'm relatively certain that all of you have seen the basics of probability. So I'm going to blow through some of the basics pretty quickly. Hopefully we're going to have fun with a little bit of an applet here in this first section and just get you up to speed if you've not seen it. If you haven't seen it, you come up to me in class, slow me down, keep note cards, keep flashcards, things like that, just to make sure that you're up to speed if you haven't seen this before. Excuse me, I'm going to take a drink. All right, so most people think probability, if I mention the word probability, it's things like let's flip a coin, let's roll a die, let's draw a card out of a shuffled deck of cards, etc., etc. That's a great way to think about it. Keep it simple. Probability can get out of hand. For those of you that have, excuse me, taken like the AMCs or the AIMEs, the probability problems in those are ungodly, but we're going to keep it relatively simple throughout this class. Remember, this is an introduction to statistics, so we're not going to get too crazy. If you enjoy this and you really want to get into it, take a class called Probabilistic Models or Combinatorics. If you can take a combinatorics class, I think you'd enjoy that as well if you like this stuff. I enjoy it. It's tricky as heck. Sometimes I just have to sit back on a problem and just go, oh my God, what am I really trying to figure out here? So if you feel like you're in the woods, you're not alone, all right? And feel free to ask questions and we can play with it. Okay, let's get the basic concepts out of the way. First things first, we're going to talk about what an event is. An event is just an outcome or collection, I'll put this parenthetically, of outcomes. Collections, that should be collection, singular, a collection of outcomes in a probability experiment. And what is a probability experiment, you may ask? It's flipping a die, flipping a coin, rolling a die, drawing a card. Having a child, believe it or not, could be thought of as a probability experiment because it comes out either male or female, although there's some interesting other things that can happen, which we'll discuss down the road. All right? A simple event, as defined by your text, is an event. Okay, Ripley, slow it down. Sorry, guys. It's an event that can't be broken down into simpler terms. It's an event that can't be broken down into simpler events. All right. Then what we've got is a sample space. Again, I'm hoping that you've seen this stuff before. Don't worry about the differentiation between event and simple event, all right? Just think of really what we're going to talk about here is just an event, okay? A sample space is the total set of outcomes in a probability experiment. Probability experiment. Okay? So let's absolutely simplest terms. Let's think flipping a coin. If I flip a coin, the events are either a head or a tail. Let's not even talk about the thing it's landing on its edge, right? That doesn't make any sense, okay? So this is one event. We call that event A, and this will be another event. Let's call that B. That's a sum total of everything that can happen. So the sample space is the set, that's supposed to be set notation, is the set HT in flipping one coin, okay? Rolling a die, now think about that. If I roll one die, a die. Fun fact, the dots on a die are known as a, wait for it, a pip. all right, or the pips. So let's see, I can roll 1, a 2, a 3, a 4, a 5, or a 6. Let's assume it's a casino die. You're in Reno, so knock it off. This would be event A, B, C, D, E, and F. These are separate events. Now, you could also think of these things. Let's say that I roll a die and I think of an event as rolling an even. Okay, so that event could be written as 2, 4, or 6. That would be the event. Or odd, then the event would be 1, 3, or 5. Now, I should probably write ors in here. This is an or an or like that. The sample space is the set of all possible outcomes in the rolling of one die. So it's 1, 2, 3, 4, 5, and 6. Okay? Now, there are two types of probabilities. There are experimental probabilities, mental prob, and then there's theoretical probabilities. Let's talk about experimental probabilities first. An experimental probability is simply the probability of something happening based on an experiment that you did. So, for example, let's say that you flipped the coin and you did it 20 times, okay? And you got 11 heads and you got 9 tails, okay? The experimental probability of getting a head in this case is 11/20. However, we know that the theoretical probability in this case is, well, it should be 10 out of 20, or 1/2. So the theoretical probability is the probability that we know that an experiment like flipping a head should play out to be. The probability that I flip a tail, or excuse me, that I flip a head on a coin is 1/2. However, if I do an experiment, I probably won't get to exactly 1/2. Think about, for example, rolling a die. Okay? Now, if I want to roll a 6, all right, so I'm going to write this as the probability of rolling a 6. Hopefully we all realize that there are 6 sides to a die, assuming that it's fair and not loaded, etc., etc. There's one way to roll a 6, and there's a total of 6 outcomes that we can have. All right. However, if I roll the die 6 times, I might not get any 6s. So in other words, the experimental probability for that experiment is 0 out of 6. I didn't get any 6s. Okay? So the way that we figure out theoretical probability is very simple. The probability of an event, I could write this as E, I can write it as A, I don't really care. It's the number of ways a thing or an outcome can happen divided by the total number of possible outcomes. Again, it's hard to write down by your belly button and not see what you're writing. All right, this is the theoretical probability. Experimental probability is easy. We just do it through observation. We look. Okay. Now, you may be saying, Ripley, wait a sec. How is that possible? How can we say that an experimental probability of an event is 0 if I roll a die 6 times and I don't get any 6s? By the way, rolling a die 6 times is exactly the same thing as rolling 6 die once. And for those of you that have played Yahtzee before, I think that's 5 dice rather than 6. Dice, excuse me, rather than 6. You know that happens all the time. Well, there's something called the law of large numbers. The law of large numbers. And this is super key. This is so key you have no idea in statistics. The law of large numbers, without the law of large numbers, statistics really wouldn't make any sense. And what this really says is that as the number of times we repeat an experiment, in this case rolling a die, an experiment, heads gets bigger, so theoretically heads to infinity, we know that the experimental probability heads towards the theoretical probability. And I have a cool little applet I'm going to show you here. Theoretical prob. It's kind of neat. Okay, watch this. Let's see. I'm going to pop out of here, and I got this applet. So check this out. What this is, watch this. I'm just going to roll it. I'm going to let n equal 1. Now, watch what happened. Basically, what this did is it rolled the die one time, and it rolled a 3. It's just a simulator, okay? So the experimental probability was 0 out of 1, which is 0. All right? Well, you may be saying, well, really, that's only one roll. Okay, now let's roll it 10 times and see what happens. Watch this. Okay, now watch this little graph. It started at 0. Okay, apparently on the second one I got a 6, so I got 1 out of 2, so it popped up to 0.5. And then on the third, the fourth, the fifth, the sixth, etc., etc., etc. Now look at this. So I've got, how many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which means that this was our first one down here. And then these were the following 10. So when it jumps up, that means I rolled another 6. Then it dropped down, I didn't roll a bunch of 6, and then it jumps up again. These are our rolls. Look at them. You can actually follow them. I rolled a 3. That's what corresponds to the 0. Then I rolled a 6. That popped up to 0.5. Then I rolled a 5, a 4, or excuse me, a 5, a 1, and a 4, which means I rolled 1 6 out of 5, right? So that's going to be around 20%. And then I popped another 6. That 6 corresponds to right there. That got it way up there. Now remember, the theoretical probability is 0.1667, which is 1 out of 6. Now watch this. This perfectly illustrates the law of large numbers. I'm going to roll this thing, whoops, I don't want 100, I want 1,000. I'm going to roll this thing 1,000 times and watch this thing get crazy. Check it out. Just watch this. Now it's rolling. Notice over here on the right, these are the rolls that you're actually getting. Now watch what's happening. As n gets bigger and bigger and bigger, watch what this line does. This little curve, this probability, it's going to have jumps, jumps, jumps. Look at this. We're at 500, what? Getting close to 600. We're above 0.1667, and all of a sudden, slowly but surely, look at her climb. Look at her climb. Or actually, not climb. Look at her descend. Getting closer and closer and closer and closer, and pow! 1011. It's 0.1682. The actual theoretical probability is 0.1667. I'm going to do it one more time, and let's see how close we get. All right? I'll just sit back and let you guys enjoy. We get so close to 0.1667 that it's very difficult to tell the difference between the experimental, which is what this thing is doing right now, and the theoretical. Watch her go. Watch her go. Getting close. 0.1716. So look at that. We had this little hump that we had to deal with. But we're zooming in closer and closer. One more time. Don't be bored. I promise. This will pay off. Oh, now look at that. She's popping up a little bit. Be interesting to see what random number generator they create. And we go. Look at this. And I love this. Getting close. Disco. 0.1667, 0.1674. That is the law of large numbers in full effect. Cool. I hope you enjoyed that. That was cool. Okay, let's go ahead and go over some rules of probabilities now that we know how to define a probability. All right? All right, first things first. We know that the probability, let's see, of an impossibility, in other words, the probability that I flip a 3 on a standard head is equal to 0. The probability, excuse me, of a certainty, all right. In other words, say the probability that I flip a head or a tail on a regular old coin is 1. And the probability of any event is always going to be wedged between 0 and 1. All right. Those are the biggies right now. I know the probability of an event, because think about it. If I also remember, the probability of an event is equal to the number of ways the event can occur divided by the number in the sample size. All right? It's also referred to as the sample space. So this guy is always going to be bigger than this guy, always, unless they're equal, which they could be. Okay? Now, real quick, let's talk about the complement of an event. Meant of an event. And we've got a notation for this. And I'm going to use a Venn diagram. This is equal to the complement of E. Venn diagrams are the easiest way to show this. All right? Check this out. Let's say that this is the sample space right here. This is my sample space. Okay, so it's the set of all the possible outcomes. And let's say that E lives over here. All right? The complement of E is everything that isn't E. All right? E complement, bless it, that just doesn't want to write on it, does it? E complement is all this stuff over here. Now, there's a really powerful little rule that we can pull out of that. If I take the probability of an event and I add that to the probability of its complement, what does that absolutely have to be? Well, think about that. The number of ways that the event can happen plus the number of ways that the event can't happen constitute the entire sample space. And if I take the number of elements in the sample space and divide them by the number of elements in the sample space, I always get 1. Okay? Now, that's just a real general introduction to probability. Now, what we're going to do here, I'm going to throw a little something else at you, especially since we're in Reno. You may or may not be from Reno. Pardon me, I'm going to take a drink real quick. But we're going to talk about odds. And the reason we're going to talk about odds is because so many people screw them up. All right? Odds, first things first, not probability. Probability. They're not probability. I cannot tell you how many times I've had somebody say, yeah, the odds of something happening are 50-50. Or the odds of rolling a 6 on a 6-sided die is 1 in 6. Incorrect. The probability of rolling a 6 is 1 in 6. The odds of rolling a 6 is actually 5 to 1 against. You could also see this written as 1 to 5. This is against, and this is in favor. Whoops, favor. Okay? Now, the odds of an event is typically written as a ratio, and it's the number of ways the event can happen as a ratio to the number of ways the event can't happen or the complement of the event can happen. That's why complements are introduced in this textbook. Now, let me explain what that really means. Odds are there for one reason and one reason only, period, for gambling. I don't care where else you hear them. The whole purpose behind odds, because if you think about it, it's just a little tweaking of the definition of probability. The whole purpose for odds, excuse me, is so that casinos know what to pay. Now, I'm going to go up on a little soapbox here, so bear with me for a sec. This won't take much time at all. Let me explain how odds work. In a fair game is defined as a game where if you play the game over and over and over and over again, nobody wins any money. The house doesn't win any money, and the player doesn't win any money. So you may win on some games, on some individual games, and you may lose on some individual games. But if you play a bunch, if you let that law of large numbers go into effect, nobody's going to win any money. It all comes out even. Okay, so let's think of this. Let's roll the die real quick. Let's play a game called Roll a 6. Okay? Now, again, the probability of rolling a 6 is 1/6. I'm going to write this again. The odds of rolling a 6 is the number of ways to roll a 6 is 1. Okay? And the number of ways to roll a not 6 is 5. All right? Notice, The odds, this ratio always adds up to the size of the sample space, as long as the ratio hasn't been simplified. Let's be real clear about that. Now, what this means is, if I am running a fair game, so let's assume that roll of 6 is a fair game. If I bet $1 and I win, the house pays off $5 plus I get my bet back. That's in a fair game. Okay? That's how odds work. Let's say we were in a game where the odds were, let's see, 150 to 1. 150 to 1. That means if I win and I bet $1, then I get $150 plus my $1 bet back. If I bet $2, then I get $300 plus my $2 back. Now, people often think that casinos somehow cheat. That's not true at all. I'm going to dummy this way down. I hope that I'm not patronizing anybody, but think about it this way. What a casino does is it simply doesn't pay true odds. In other words, in my game of roll of 6, clearly a casino doesn't have a game this simple, but pretty close. In the game of roll of 6, if I win, they wouldn't pay me my full $5 back, plus my bet back. They may pay me a total of $4, which really means that they're giving me 1 to 3 odds, because remember, there's my $1 bet. So if they hand me $4 back, that means they gave me $3 plus my $1 bet back. That guarantees that over the course of many, many, many plays, the casino, even when they pay out, they're actually making $2 over true odds. And that's what true odds are. Okay? Those are what are referred to as payout odds. These are payout. Whoops. I'm sorry, I should have pointed to that. These would be payout odds, and these would be true odds. So these are true, and this is what the casino might pay out on. And that's how the casinos make a lot of money, keep their lights on, and employ a bunch of employees. All right, I hope that was helpful. We'll play around a lot more with probabilities. They're a good time. Thanks for paying attention. Okay, so let's get some more rules. There's going to be some rules in this, but believe it or not, there aren't that many rules in probability at all. But man, the combinations can get out of hand really, really fast. Okay, first rule is, let's talk about the probability of an event A or the probability of an event B. So think of this as if I have, what's the probability of rolling a 6 or drawing a jack from a deck of cards? Now, the most important question when you answer these types of problems is, are the events mutually exclusive? Mutually exclusive. Another word for mutually exclusive is, I can't hear you, disjoint. Okay, disjoint means they can't happen, they don't overlap. They can't happen simultaneously. In other words, what I'm doing is I have a die in one hand and I have a deck of cards in the other. And I roll the die and I draw a card with the other. They don't overlap at all. So let's think about that. What I've got, if I think of this as a Venn diagram, I have two sets. I have the die set, and that's got 1, 2, 3, 4, 5, 6, and then I have the card set, and they don't overlap. There's nothing overlapping. Now you may say, wait a sec, but Ripley, what about the 1 of hearts? Because this would be ace through king of hearts, ace through king of spades, etc., etc. So this is ace through king 4 times. Okay, well, they're different outcomes. We're counting pips in this case, and we're looking at numbers on a card. So this 2 on the die is not the same as the 2 that you would draw out of here, because the experiment is different. They are disjoint. They have no overlap. So the rule for that, for disjoint events, is you simply add the probability of A plus the probability of B. So in this case, the probability of rolling a 6 on one die is 1/6, plus the probability of drawing a jack is, well, there's 4 jacks in a deck, and there are 52 cards, so this is 4 52ths, affectionately known as 1/6 plus 1/13. What is that? 19 60 78. So 19 78. That looks about right. All right. So what is that? That's about a fourth. Okay. Now this only happens when my sets are disjoint. Now let's go back. Let's go do cards this time. Let's do the probability of a heart or a jack. All right. Now before we do this, let's build. We got a deck of cards, and I'm finding the probability that I draw a card, and that card is either a heart or a jack. Well, you've got the set that represents all the hearts in the deck, and then you have the set that represents all of the jacks. Now there are 4 jacks in here, but this intersection between these two sets is, as you can well imagine, the jack of hearts. There's a jack that is both, or excuse me, there's a card that is both a jack and a heart. Now there's 12 other cards in here that aren't jacks, and there's 3 other cards in here that aren't the jack of hearts. But the problem is if I apply this rule, this counting rule, or this probability rule, watch what would happen. I would say, okay, the probability of hearts plus the probability of a jack. The problem is that this card got counted twice. It got counted in the hearts, and it got counted in the jacks. So what we need to do is we need to subtract out the probability of the jack of hearts, the probability that it occurs at the same time. Does that make sense? Think about that for a sec. The jack got counted in the jacks, but it also got counted in the hearts. So there were 13, think about it this way, there were 13 out of 52 hearts, and there were 4 out of 52 jacks, but the problem is the jack of hearts got counted in both sets. So I have to subtract out one of those times that it got counted. All right, so stew on that for just a second. So what was that, 17, that's 16 52ths or 4 13ths. All right, in this case, a little bit less than a third. So what we need is a rule. So let's see, let's write my rule right down here. The probability of A or B, now in this case, we're not mutually exclusive. We have overlap. All right? The probability of A or B is equal to the probability of A plus the probability of B minus the probability of, now if we do set notation, it's the intersection, but you'll also hear this referred to as the probability of A and B. All right? So everything that these rules speak to depends on whether or not the sets are disjoint or not. Now, the conjunction that we want to play with here is or. I am saying the probability of something or something else happening. This, let's call these the or rules. The or rules, right up here. What I'm going to get into next is the and rules. And rules. And rules sounds like androids or somebody drools. And rules, put a little parentheses so it doesn't sound so goofy. The and rules have to do with something called independence, or dependent. All right? Okay, now, let's start nice and simple. I want to figure out the probability that I flip a head on the first coin that I flip. So I'm going to take a coin, I'm going to flip it 3 times. Okay? I'm going to flip a head on the first coin, and I'm going to flip a head on the second coin, and I'm going to flip a head on the third coin. Now, the first thing that we need to do before we talk about these types of problems is we need to discuss something called the fundamental theorem of counting, or principle. Principle. That's the guy that runs the school, or gal, as it may be. Let's see. Principle of counting. what I need to do is figure out the size of the sample space when I flip these three heads, or excuse me, when I flip these three coins. The fundamental principle of counting says that if I have two outcomes on the first flip, and I have two outcomes on the second flip, and I have two outcomes on the third flip, since I'm combining all three of these flips to make a head on the first and a head on the second and a head on the third, I multiply them. So the size of my sample space when flipping three coins is 8 separate outcomes. And we could actually list them all. I mean, check it out. If I go, let's see, I could go head, head, head. I could go head, head, tail, head, tail, head, tail, head, head, tail, 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 head, tail, head, tail, and head, tail, tail. Total of 8, just like I promised. The types of fundamental principle of counting problems that you may have seen is, let's say that there are 4 salad choices at a restaurant. There are 5 entree choices at a restaurant. There are 3 dessert choices at a restaurant. How many distinctly different meals can I make? Well, it appears that there are 4 times 5 times 3, which is 60. That all has to do with fundamental principle of counting. And it's really helpful for us when we're trying to figure out sample spaces, especially in AND problems, because we're building something that happens simultaneously. We're building a 3-coin problem. All right, so think of flipping flipping a coin 3 times is the same thing as flipping 3 coins. But if 3 coins fall in front of you, there's no real order implied in that. But we need to really think of this as being a different order. So think of it as flipping a penny, a dime, and a quarter all simultaneously, because then that order comes into account. Okay, so let's go back to this guy right here. Let's go. I'm going to kick over a page just to have myself a little bit more room. So the probability of a head on the first, and I'm going to get shorthanded with that here in just a little bit. There's a shorthand for and that makes it simple for lazy guys like me. All right. Now, the first question that you have to ask is it independent? In other words, let's talk about independent events. Events are independent if they don't affect each other's probability. All right. In other words, if I flip a head on the first coin, will that have anything to do with the probability of me flipping a head on the second coin? I'm hoping that you see that the answer to that is absolutely not. Okay. Now, think of another independent event as if I take a deck of cards and I shuffle them up, and I do, let's see, the probability of, I want to know that the probability of getting a jack on the first, and if I get a jack on the second, but I'm gonna replace. So with replacement. In other words, I'm going to replace the card after I've drawn this first card right here. So I draw a card, and I look at it, and then I stick it back in the deck, and I reshuffle. All right? Now, notice that there's 52 cards for the first jack, and there's 52 cards for the second jack. So the probability of those are not affected at all. So if I get a jack on the first, the probability of getting a jack on the second is not affected at all. Now, if they are independent events, the fundamental principle of counting is in full effect. We get to use that little piece of information, and all we do is we take their probabilities. The probability that I get ahead on the first one is a half. The probability that I get ahead on the second one is a half. And the probability that I get ahead on the third one is a half, and I end up with 1/8. Now, we actually did that graphically over here. Look at this. When I listed my sample space, isn't that the outcome that we were looking at for this probability? Woohoo! There is one way to get 3 heads, and there are 8 total possible outcomes in the sample space. Guess what? 1 in 8. For the jacks problem, let's do that one real quick. Whoa, where's my pen? The jacks problem, there are 4 out of 52. And there are 4 out of 52 because I replaced it. But this is really 1 out of 13 and 1 out of 13. Because I replaced it, that implies that the events are independent. So I get 1 out of 169. That's the probability. Now, I'm going to flip. So I'm going to go back to a problem that we did with the or statement. Now, watch this. I'm going to do exactly the same thing. Let me change colors real quick. Looky here. Notice here I wrote the probability of getting a heart or a jack. So really what's happening is I'm doing 2 things at once, but I'm really looking for the probability of either one or the other. Now watch what happens if I bring this over and I go the probability, wait, I'm sorry, back that up. I apologize. A 6 or a jack. I'm rolling a die and I'm drawing a card, but I'm saying or. It's one or the other. All right, or both, but I can't count it twice because I use that or statement. Over here, if I write this as the probability of a 6 and a jack, notice that conjunction is really, really important. It's the cornerstone of figuring out probabilities correctly. That's a whole different ballgame. Now, they are still independent of one another. If I roll a die and I get a 6, it does not affect the probability of drawing a jack out of a deck of cards. Likewise, if I get a jack out of a deck of cards, it doesn't affect the probability of rolling a 6 on the die. But the thing that you have to understand is that when I roll the die and I draw the card, what I'm looking at is a 6 on the die. Oh, I'm going to screw this up big time. A 6 on the die and on the card, a jack. Now, it could be any one of the 4 jacks, but because they're independent, I simply multiply their probabilities. The probability of getting a 6 is 1/6. The probability of getting a jack is 4 out of 52. There are 4 jacks out of a total of 52, or 1 out of 13. And what is that? That's 1 out of 78. There are 78 total outcomes in an and statement like this where I roll a die and I flip a card. We could list them if we had more time, but we don't. All right? Now, I know the question that's nagging in the back. Whoa, what just happened there? I hit the wrong button, apparently. I know the question that's nagging in the back of your head. And that question is, well, what if they're not independent? Let's go back to here. Well, then they are dependent. So let's say that I want to find the probability of jack on the first and jack on the second. Now, in this case, we're going to do this without. Let's go without replacement. In other words, I draw a card and I get a jack, but I don't put the card back in the deck and reshuffle it. Okay? The probability of getting a jack on the first is 4 out of 52. But on the second one, now remember, I'm still making what is ostensibly a 2-card hand. The probability of getting a jack on the next one, well, think about this. How many jacks are there left? There's 3. How many cards are there left? There's only 51, because I already burned one of my cards here. All right? So the probability of getting a jack and a jack in a 2-card hand, if I flip them up one at a time, is, oh, good gracious, how the heck am I going to do it? You know what? I'm lazy. I know it's 12. Let's see. Oh, sorry, you guys. I don't mean to be too lazy, but it's getting a little late. 12, 26, 52ths. 12 out of 26, 52. So if I use my fancy math and I go to, I think I can reduce it. 1 out of, this is 1 in 221 times. Which means, excuse me, if I take a deck of cards and I flip up 2 cards, the probability that both of those cards are jacks will happen 1 in 221 times. Now here's a little food for thought. What are the odds that it happens? Well, if the probability is 1 in 221, then the odds, where's my pen? Wow, I'm way off of there. Then the odds, the number of ways that it can happen is 1. The number of ways, this represents a reduced sample space of 221. If I pull one value out, it's 220 to 1. Which means if we're playing a game and I win the game and I bet $1, I get $220 plus my $1 back. Okay? Okay, so what we need is some good old-fashioned notation here, okay? And I'm going to give that to you right now. So let's do this first. For independent events, the probability of A and, I'm going to underline that, B, is equal to the probability of A times the probability of B. All right, just like we did before. For dependent events, I'm getting better at writing. No, events, or not. There's an oh good God, let's just call that an event. Can we agree? The probability of A, notice again, and versus or, that's really, really key, is equal to the probability of A times the probability of B given A. Now this little thingy-dingy right here is given. Now let me explain what that means. This probability right here, really, we can interpret this as this is the probability of a jack given a jack drawn on the first card. Sorry about my craziness right here. Okay? Probability of B given A. But the key is that conjunction. If it's or, you've got a whole different set of rules and you've got a whole different set of questions that you have to ask yourself. The or rules is it mutually exclusive or are they disjoint? Are the sets disjoint? Probability of A or B, if they are not mutually exclusive, you've got a different formula. If you're looking at an and, the problem is that the examples, which we'll do a ton of these in class. Remember, I'm just giving you the information right now. The problem is the way in which problems are written, you can't always tell. It's difficult to tell whether it's an and or an or statement. But before you can proceed at all, you have to know whether it's an and or an or statement. Okay? Well, that gives you some rules. That's really, believe it or not, that is the total of all of the rules for probability. It really is. They get more complicated when we start mixing and matching and if we do a whole bunch of different things. Like, for example, let's say that the probability that let's make a 3-card hand. So let's say the probability that I get a heart on the first one and a heart on the second one and a heart on the third one. Now, hopefully you see these ands, and the first question that you ask yourself is this with or without replacement? Because that would imply independence. Let's say that this is without replacement. Okay, well that's easy. I know that there are 4 hearts in the deck and there are 52 cards, so it's 4 out of 52. For the next one, there's only 3 hearts left. There's a total of 51 cards left. And for the last one, there's a total of 2 hearts out of 50, and then we do our thing. However, if it's with replace, then it's going to be 4/52ths, sorry about my notation here, times 4/52ths times 4/52ths, because I keep sticking that card back in, or 4 out of 52. 4 out of 52 cubed. All right? We've got some really good formulas to work with, and believe it or not, there aren't any more formulas that pertain to probability left. That's all we got. Hope you enjoy.